Okay, so now we're running into the question, what about things like fractions, the rationals that are not the natural numbers, right? What about, so we've discounted the negatives as being numbers because they're vectors, because they have a direction, right? So the difference between 3 and -3 is its direction. So the difference is a vector element that's not part of the number. It's part of the vector. It's part of the thing that defines it as a vector. It's the unit, right? Okay, so we don't have negatives in our numbers. We don't have positives either, right? So if I'm talking about numbers and I say 3, it's not positive 3. It's 3. Positive is a unit. So it's not positive, it's just 3, right? There's a difference here. Now, what about something like 2/4? Right, so say, we're looking at an object. For simplicity's sake, let's make it like a pizza or some shit. What the quarters means is that we took our object, our one thing, and we cut it into 4 pieces. And the 2 means that we took 2 of them. Right, so we took this one, and we take this one. And that gives us our 2. Okay, so this 2, come on now. All of the things to see are down here, silly camera. This 2 is actually describing how many of these we have. So this is a unit. So to consider this to be a number is strange because this is the number of these that we have. Okay, so the whole thing, is it really a number, or is it really the same trick that we did with the negatives, where this part is the unit, or the denomination, hence the denominator, and this part is the number, or the numerator, right? Numerator, denominator, number, denomination, number, unit. I don't think these are really numbers. And so we can actually bring this into sort of a real world consideration. So say we've got a lake, right? Come back to the lake. So we've got, there's our little lake. Okay, so it's a hole in the ground filled with water. That's our lake. Okay, what does it mean to have half of a lake? As far as, like property rights or something, you can do that. But as far as the physical object, you cannot do that. You cannot subdivide this into fractions of a lake. That doesn't even make sense, right? So say we've got a property line that goes through like this. Okay, so over here we have George, and over here we have Suzanne, and Suzanne owns this half of the lake, and George owns this half of the lake. Okay, legally speaking, that makes sense, but it's really the same lake. The water is shared, the fish are shared, whatever. This is not a hard boundary in any way. If we make this a hard boundary, say we drop in like a wall or something, like a big wall of sand to actually divide this physically. Well, now we have 2 lakes. We cannot make half of a lake. That doesn't make sense. Okay, so half isn't a number of things you can have, right? Take an apple, right? Bing bong. There we go. Take an apple. What happens if you cut it in half? You have half an apple? Yeah, I guess. But if, say, on the tree, there was an apple where like some of it had been eaten by birds, would you say it's half an apple, or would you say it's like a fucked up apple? You're probably not going to describe that as half an apple. You're probably going to describe it as an apple that we're going to throw away. It's trash. It was destroyed by birds. So it's not clear to me that fractions are actually numbers, right? Now, what about things like the irrational numbers? So like a nice simple example, I don't know what you're doing, camera, is, say here we have, this has a length of 1, this has a length of 1, this has a length of square root of 2. There. So that relationship from 1 to square root of 2, are those really numbers? Is that a number? Is that a number? Is that a number? Again, I don't know, because what we can do is we could just restructure it so that's 1. And this is now root 2 on 2. So this doesn't actually mean anything. The 1 doesn't mean anything. So if the 1 doesn't actually mean anything unto itself, neither does the square root of 2 or the square root of 2 on 2. These aren't real. It's the relationship between the lengths of this 1 and this 1. They're both really just 1. Right? So if we kind of go back to our sense of 0 is nothing, non-existence, and 1 is something, I'm just choosing my reference frame. Which something is my basic something? That is a completely arbitrary choice. I can choose this to be my basic something, or I can choose this to be my basic something. And then we enter into, we're now operating with vectors, and we can do vector manipulations, which is, arithmetic and those sorts of operations. But fundamentally, I can only operate with ones. I have to start by defining what my units are. I have to define my units to start with, and then I can count them. And I count them with numbers. But once the units are involved, it's not a number anymore, it's a vector. Right? So this 2/4, it's really the same as these 2 lakes. That 2, it's the same 2. Right? So, yeah, I don't think square root of 2 is actually even a number, because we arrive at it arithmetically. What about pi? So, say we have a circle. There's a beautiful piece of shit circle. Okay. So what we're going to do is we're going to compare the width, let's say that's 1, to the walk around. Now that's pi. Well, we could just change that. We could convert pi to 1. We could say that walk around is 1. And now this becomes, well, 1 on pi. Right? Because if I take this and multiply by pi, I get 1. If I take this and divide it by pi, I get 1. Right? So it depends. Again, it depends. Also, this is a straight line across the circle, and this is this weird curved line. So they're different things in the first place. So it's weird to even compare them at all, You have to do some unit conversions to even get this comparison. And if you're doing unit conversions, you're operating with vectors, not numbers. So in order to go from 1 to pi, in order to even find pi, we have to step outside of operating with numbers in the first place. Also, why is pi special? Why are we not looking at 1 on pi? Why is this one more special than this one? You run into all sorts of these questions because the way that it's being looked at is just fundamentally wrong. So I would say that your numbers are actually just your natural numbers. Your natural numbers are your only numbers, right? So 0, 1, 2, 3, etc. Like the things that you can count, right? I can have 3 people, $3, 3 lakes. 3 is a thing that I can have in pretty much anything. Pi is not a thing that I can have anything of. So it's special in some sense. Square root of 2 is not something that I can have anything in. How do you have square root of 2 apples? Does that make sense? How do you have square root of 2 lakes? How do you have square root of 2 holes in the ground? I can have 1 hole, or no holes, or 2 holes, or 3 holes, but I can't have square root of 2 holes. I can't have square root of 2 dogs. That doesn't make sense. These aren't numbers. I can't count to this. This is something that arises once we're working with vectors. So this is fundamentally a vector. It's built into it. It's a vector naturally, as is pi, as is 2/4 or 1/2, or which are the same thing, or kind of. They're kind of the same thing. You can see it's not exactly the same thing. Like, sure, I removed half of the pi, but I did it in a way where the 2 actually means something. It's different than taking this, right? This 1/2 and this 2/4, they're not the same. Okay, so this is not the same as 1/2. It's different. And the reason that it's different is because the units, the fundamental units, the 1/4 and the 1/2, are different from each other. So these are not entirely commensurate with each other. The units, right, so this is 1/2. The denominator is actually giving you information. But in school, when you're taught about fractions, you're taught to ignore that and throw it away and that it doesn't do anything. But really, it's obvious that it does. And when you just look at this, if I cut a pie this way, right, and we take these 2 dark slices, and I cut a pie this way and we take this dark slice, something different happened, right? We're working with different units. This is a different vector manipulation on this than this is. But we're taught to ignore that because these are the same number. They're not the same number. They're not numbers at all. They're vectors, and they're different vectors from each other. They are distinct from each other. If all you're doing is abstracting away to how much was removed or how much is left, yeah, in terms of like that sheer quantity or volume or something like that, yeah, they're the same. But that requires a further vector manipulation, a further abstraction, a further unit conversion, which, right, like, originally that's not really describing what happened. That's an abstraction. This is also an abstraction. This is an abstraction, right? The real things that you can count, the numbers, are these guys. The natural numbers. And that's it. Those are the only numbers there are. As far as numbers go, I think. This is it. Those are the only numbers. Everything else is vectors.